So in the previous two videos, we've been talking about eliminations and E1 and E2 eliminations and comparing them to substitutions. What we're going to move into now is looking at a particular functional group, the alcohol, and kind of how do we use the alcohol? Because alcohols kind of show up in SN1, they show up in E1 reactions, they show up in E2 reactions, and all throughout this. And so how do we kind of use an alcohol as a guidepost to kind of help us through each type of these mechanisms as we get there? Okay. And the answer is basically the alcohol is pretty unreactive on its own, but we can manipulate it to do whatever we want, right? So let's talk about alcohols. All right, so here's your standard garden variety alcohol, right? It's got an OH group there. This oxygen has two lone pairs. So what we know about alcohols is that they're generally not very nucleophilic. They're not good nucleophiles because not very nucleophilic, right? They're not good nucleophiles because that oxygen is so electronegative, it doesn't want to share its electrons. We also know that an OH group is not a good leaving group because if we break that carbon-oxygen bond, we create O-, and we know that O- is not a stable conjugate base. O- is usually actually a pretty strong base, right? And so we have this compound that's not very nucleophilic. It's not a good leaving group. Alcohols in general are not very acidic. Right? They're pretty close to neutral. They're mostly just like water, right? And so we don't have an acidic hydrogen. So unless we react them with strong base, they don't usually give away H+, and they're also not very basic, right? The conjugate, so think about what is the conjugate base is going to be a negatively charged oxygen, right? The alkoxide, and so that's going to be pretty reactive. The conjugate acid of an alcohol is going to be maybe even a little bit worse in that it's going to be a positively charged oxygen like that. And so neither the conjugate base nor the conjugate acid of an alcohol is particularly stable. And so the equilibrium of these acid-base reactions will almost always favor the neutral alcohol. And so when we talk about alcohols, really what we're talking about is a functional group that is not very reactive. And so then you might ask, well, why are we even bothering to talk about it then? If we're interested in reactions and we want to talk about alcohols, right? Like, or we want to talk about things that do reactions, why are we talking about alcohols? And the answer is that we can activate these alcohols and make them more reactive. So the key to alcohols is that we always take one step to make them more reactive. Okay. So the first example that we're going to do of this is we're going to talk about how do we use alcohols in E1 mechanisms. Alcohols in E1 mechanisms. This is called a dehydration. So we're going to lose water. All right, so let's take, we'll just use cyclohexanol. That's a nice alcohol that we can use. We're going to do an E1 mechanism, and so we're going to create a pi bond where we had sigma bonds before, so we're going to get to something that looks like this. Right? And the way we're going to do this is we're going to treat this with strong acid. So you'll often see this done in like H2SO4 or something. And remember that H2SO4 is just a fancy way of writing H+. So, and importantly here, it's not just H+, it's a very, very strong acid, right? We're using sulfuric acid, which is an incredibly strong acid. And so we're getting something that is going to react even if our alcohol is not a very good base, right? So even though we talked about how alcohol is not a very good base, in the presence of sulfuric acid, this is the best base around, and so that oxygen is going to go pick up that H+. So this first step here, remember on the previous slide I said the first step, we always take one step to activate the alcohol. This is our activated alcohol, right? So in this case, it's our conjugate acid. And now the equilibrium for this reaction is dependent on whether the neutral cyclohexanol or the negatively charged HSO4 minus conjugate base of sulfuric acid is more stable. And that's actually a pretty close thing. Sulfuric acid is an incredibly strong acid, and so the equilibrium actually ends up favoring this activated alcohol. And now the question is, what is this activated alcohol going to do? Now, we don't want to have, oxygen does not want to have a positive charge on it, and so what it's going to do is it's going to pull electrons toward itself to the point that it's actually going to break away from the cyclohexane ring, and we're going to be left with a secondary carbocation plus water. And so what we've done, our activated alcohol has become a good leaving group. This is a trick that we're going to use over and over and over again anytime we want to make an alcohol a good leaving group. Remember that alcohols are not good leaving groups to begin with, right? If we want our alcohol to leave, we need to treat it with strong acid. Because what that strong acid will do is it will make it an activated alcohol, it'll turn it into a positively charged oxygen, and that will be a good leaving group where it can leave as water, a nice stable conjugate base. Now we have a carbocation here, and so the question is, what is this carbocation going to do, right? What do carbocations do? An exhaustive list, right? One, they rearrange, right? So anytime we make a cation, especially a secondary carbocation like this one, we have to check, is it going to rearrange? In this case, it's not, because it's only neighboring two secondary positions. So this can't become a tertiary cation, so this one's just going to stay there. The other thing it can do is it can do SN1 reactions, or it can do E1 reactions. And those are really it. So anytime we make a carbocation, we should immediately have this list where we talk about, does it rearrange, or is it going to do SN1, or is it going to do E1? If it does SN1, right, this water will come in, right? This water can come in and attack this carbocation, and the product that we would get out of that would be this, our activated alcohol again, right? And what is that going to do? That's going to lose water and just become the carbocation. So it goes back and forth here until eventually we remove the hydrogen from the neighboring position and make our pi bond and do our E1 elimination to get our double bond.